Hello students, welcome to this JE Advanced Review series. Today we'll discuss a few more questions on the heat chapter. So let's start with the first question. This question is a nice adaptation of a question that appeared in Olympiad. So let us try to understand what the question statement is. It says that water is being heated in an electric kettle. At a certain moment of time, a piece of ice at 0 degrees Celsius was put into the kettle. Now, the figure depicts the dependence of the water temperature as a function of time. Now, you need to calculate what is the mass of the ice, and the heating power of the kettle is given 1 kilowatt. The latent heat for melting of ice is given, specific heat of water is also given, and the room temperature is 20 degrees Celsius. And the slope of the graph at the point A is given 0.24. So from this data, you need to calculate what is the mass of the ice that was put into the kettle. So you just pause the video here and take your time for 4 to 5 minutes and think about it. Try to solve this question, again come back to see the solution. Okay, so welcome to the solution of this question, and let us first go to the solution page. So this is the solution of this entire question. I have written a few things that I will explain. So first of all, we need to understand why this graph is not a straight line. So if I am heating water with electric kettle, the power of the electric heater is constant, but the water temperature does not rise uniformly or in a straight line. The reason is that water is not only taking heat from the electric kettle, but it also releases heat to the surrounding. As the room temperature is mentioned and the water temperatures are also given, so we can say that the temperature difference between the surrounding and water is small, and we can use Newton's law of cooling in order to find the rate at which the heat is dissipated by radiation, right? So let me construct an equation with this. So before ice was put, power P of the kettle minus K into T minus 20. So what is K? It is a constant, and T minus 20 is the temperature difference. So as we know that the power of the radiation directly proportional to the temperature difference of the surrounding and the body, right? So at any instant, if the temperature of the water is T, then the difference is T minus 20. This is the heat radiation to the outside, and P is the heat coming to the water, and that will the together of these two power will rise the temperature of water with the formula M into S into dt by dt. So I think this equation is clear to you. So before the ice was put, definitely you can see that at this time 175 second, you can see that these units are 25 divided like this. 0 time equal to 0 second, 25 second, 50 second, 75 second, like this, and the temperatures are increasing with 20 units 10 units for each of the grids. So 20, 30, 40, 50, 60, 70, like this. Alright. So why these blue lines are drawn, what is the significance of that red line, each and everything we will understand. So the first thing is that at T equal to 0, the water temperature was also 20 degrees Celsius. So this part was 0 at T equal to 0, right? Or we can, in order to find out the equation of the graph, we can understand that t minus 20 is t prime, suppose, because this axis is t prime axis basically, right? Let us name it t prime axis. Now it becomes t prime axis. So t prime starts from 0, not 20. T prime starts from 0. I can write this equation as p minus kt prime is equal to mws, and as t prime and t has a simple equation, so dt by dt is dt prime by dt. Now you can see that if I take this term in the denominator of dt and dt prime, and then take this time dt here, and then I can integrate, so I will find a exponential equation. Definitely it is not a linear equation. That is why the graph is not linear, right? So once I put the ice here, now the water temperature comes from this 73. Look here, this temperature is 73 degrees Celsius. This blue color horizontal line shows you 73 mark, and this temperature is 67. So what happens? The water temperature was increasing as soon as I put the ice here. Now the water is busy sending heat to the ice, right? So as the water also sends heat to the ice, and parallelly it also dissipates the heat to the surrounding as it was doing earlier, and definitely the power electric of the electric kettle is sending the heat to the water. So in effect of all these three, now the temperature of water decreases, but it decreases up to this 67 degrees Celsius. After that, you can see that this graph again comes back, and it again goes on increasing the temperature. So I have written here that after ice was put, water temperature comes from 73 to 67 degrees Celsius. And how much is the time interval? It is definitely 25 seconds. So in 25 seconds, water temperature comes from 73 to 67. Let us try to form an equation with this. This equation will be that in time tau, the water heater has sent a total heat energy P into tau to the system. With this energy, the temperature of water has come down from 73 to 67, right? So that should be negative sign before it. Water temperature has come down from 73 to 67, and ice temperature has gone up. First, ice has melted, Mi into L. Mi is the mass of the ice, L is the latent heat, and plus Mi into S into 67 minus 0. This Mi is the mass of ice, but it is in the form of water. And simultaneously, the heat is released to the surrounding by the radiation. And that will be the same constant K into 70 minus 20 into tau. So why I have written here 70? Probably you should remember that we have done in class. When Newton's law of cooling is applied, we take the average temperature of the body, and the average temperature of this water coming from 73 to 67 is 70. Near about 70, I have taken the average temperature of the water. As the time interval is very small, 25 seconds, so I can, and the temperature difference is also very small, I can anywhere take the average temperature in order to use this formula. So I think this formula is clear to you, this equation. And now I will just modify this equation. So Mi, mass of ice, into L plus 67S, that must be equal to P into tau, the energy provided by the kettle, minus K into 50 into tau, and when this will come the left hand side, that will be plus. So here I have written the correct expression. Here I forgot to mention that minus sign. Right, so this is 6, and when it will come here on the left side, MWS into 6 will be there. You can see that this equation I know few things. I have to calculate few things, and I can calculate what is mi from this equation. So let us first go back to the first equation. If I have to calculate what is mw into s, this is mw into s, right? Sorry, this should be mw into s, right? mw into s. What is the value of mw into s? That I can calculate from here, because at initial condition when temperature was 20, this term vanishes. So mw into s, mass of water into s, specific heat of water into dt by dt, that is equal to P. So let me write it here from equation 1, m water into s equal to P divided by dt by dt, which is the slope of the temperature versus time graph when the temperature is 20. So this red color line will give you the slope. You can see that this red color line is drawn as the slope at this point, and you can easily calculate that this height is 1 2 3 4 5 units. Each unit is of 10 yes, 10 degrees Celsius. So this is 5 into 10 50 degrees Celsius, and the base is 4 unit. Each unit is 25, so this is 100 second. So 50 divided by 100, that is the slope, which is half. So I can say that mw into s equal to 2p. I will use this later. mw into s equal to 2p. That we have calculated. Okay. So moving forward, this equation, out of this equation, we know mw into s. So this value is known. P is known. Tau is known. I do not know what is k into 50 into tau. Right. Look, one more thing here, it is given that I want to calculate this value, na, k into 70 minus 20 into tau. Forget about this portion. When you are at this point A, what is the slope of this graph at point A? Slope of this graph at this point A is nothing but this one. You can see that again I am coming to the equation number 1, that at point A where the temperature was 70, look, the temperature is 70 here. At point A where the temperature is 70, so P minus K into 70 minus 20, which is 50, which is equal to mw into s into dt by dt. Right? So I can say that P minus K into 50, that is equal to mws into the slope at this point A, which is mentioned in your question as 0.24. 0.24 means 6 by 25. Right? Now I will again rewrite the equation, which says mi into L plus 67s equal to mw, mass of water, into specific heat, multiplied by, I am now taking this together, and this entire value is mws 6 by 25 into tau, and there will be another plus mws into 6. Now tau and 25 will cancel each other, and both the terms is now mws into 6. So it is 2 into mws is 2p from here, from this equation, multiplied by 6. So that is 24p. 24p. P is again 10 power 3 watt, because the 1 kilowatt, so it is 10 power 3 watt, and L is 335, and 67 into S is 4.2. Right? Those values are also given in kilojoule per kg. So I have multiplied into 10 power 3 joule per kg. So joule gets cancelled out. So the term, now the unit of this term is only kg. So you can see that this denominator part will be nearly 600, right? Because this is 335 and this is, even if it is 70, so 280 I can say roughly. So 280 plus 320 is 600, so it's more, slightly more than, it will be 600 like this. So 600 and this is 24, right? So if I cancel with 6, so it is 4 by 100 means 4 by 100 kg. So 40 gram, it's near about 40 gram. So the closest answer option is 39 gram. So option D is your correct choice for the question. I think that you have understood the entire solution. Even if you have any doubt regarding this particular solution, or any doubt regarding the theory of this particular solution, you can always leave those doubts in the comment box below, so that I can reply whenever I get free time, and from your comment also other students can learn. So let's go to the next question. I have taken this question from a book called 200 Puzzling Problem in Physics. And this question is a nice question which is based on the thermal radiation. The question says that a totally black spherical space probe is very far from the solar system. As a result of heating by the nuclear energy source of strength I inside the probe, its surface temperature is T. The probe is now enclosed within a thin thermal protection shield, which is black on both the sides and attached to the probe surface by few insulating rods. Determine the surface temperature which would result from using n such shields. So the question says that this is a probe or any space shuttle, something like that, and inside there is a power source, and it says that the power source is some nuclear energy, suppose, whatever it may be. So I have assumed it to be a power source, and this is constantly supplying I watt power. Due to this, the temperature of the surface of this spaceship is temperature T. And this is a black surface, means it can be a black body, you can assume. Now what you do, you just enclose this spaceship with a black surface, a spherical black surface that is not touching the actual surface of the spaceship, and these are few insulating rods which are separating this outer surface to the inner surface, and this is also a black surface. Now due to this, what will be the temperature change of the surface of the spaceship? You have to find the answer for n such surfaces. If I apply n such surfaces, what would be your answer? But I will suggest you to do it for a one surface. You can understand what is happening. Then you can generalize the situation for n such surfaces. So take your time and again come back to see the solution. So this is the solution of this question. Also, this question seems to be a tough one, but the solution is not that tough. You can understand it easily. Let us first consider this spaceship when there was no enclosed surface surrounding it. So the inside power was I watt, that was generated by the nuclear power, and the surface, the outside surface, if the temperature is T, it was radiating heat energy by the formula sigma into A T1 to the power 4, if the T1 is the temperature of the surface, right, which is given as temperature T. So the temperature is T and the outer surface is emitting the power sigma A into T1 power 4. You can say that inner surface is also emitting heat radiation, yes, definitely, but inner surface, whatever they are radiating heat, all these heats are again falling back to its own surface, right? So the power that is leaving from the surface, again the same power is coming to the surface. So they are cancelling each other. I do not have to take the inner surface power. Only the outer surface power is emitted, a net loss of power from the outer surface is there, and net gain of the power is from the power source, nuclear power source. they must be same in steady state, right? Even if it is not mentioned, you always assume a steady state. So I can say that sigma a T1 power 4 equal to I. Now come to the next case, when I have enclosed that spaceship with a thin shell. Remember, I have drawn the radius to be different, but the enclosed shell is very close to the spaceship, so that the radius of both of them we can assume to be the same. Now, what are happening here? Just try to focus on the diagram. Look, I power is still there inside, right? And this surface is now sending some power outside. It is a black surface, black body, it is sending some power outside. And if I say that its temperature, body temperature is T3 now, then the power that it is sending will be sigma into A into T3 to the power 4. Remember, I assume that the temperature of that enclosure is T2. What happens now for that enclosure, as it is also a black body, it will emit heat radiation both outside and inside, right? And now the inside, the heat radiation that it is emitting from the inside surface are directly falling on the inner spaceship or the outer surface of the spaceship. Because the distance are very small, this energy will directly fall from the inner surface of the of this enclosure to the outer surface of the spaceship, right? And as the spaceship also a black body, so it will completely absorb that heat radiation, and that yellow radiation that the spaceship releases will directly fall onto the inner surface of that enclosure, and that enclosure will also absorb that entire heat radiation, as it is also a black body. And the outer surface of the enclosure also sends some heat radiation, as the temperature is T2. I think it is clear. These three radiations you have to understand. One radiation is sent by the spaceship outer surface that falls to the enclosure inner surface. One radiation is emitted from the enclosure inner surface, completely absorbed by the spaceship outer surface. And another radiation is emitted by the enclosure outer surface, and it does not come back, it goes to the space. Okay, now what equation I can write? For the outer surface, when I write down the equation, it should be sigma A T2 power 4 is equal to I. What is sigma A T2 power 4? It is the heat radiation from the outer surface, as it is a black body. So E is equal to 1. So sigma A T2 power 4 is the heat radiation from the outer surface. Now why it is equal to I? The reason is the source of the power is only I. These are not the source of power, right? So even if you cancel this outgoing and incoming, you will find the same value of I, right? So as a result, if I say that what is the net power that is input to the system, that is only I. These are not the input power, right? And that input power is equal to the output power, and output power is equal to sigma A into T2 power 4. And now from this equation number 1 and equation number 2, I can say both are I. So T2 is equal to T1, and that is equal to temperature T, right? Here T1 is equal to T, as mentioned in your question. The same equation, when I try to write down for the spaceship, I can say that the power that is coming to the surface of the spaceship are only coming due to the source I, and the power are coming also due to this inner surface of that enclosure, which is sigma A into T2 power 4, right? I have assumed that area to be the same everywhere because the radius are very close to each other. So sigma into A into T2 power 4 plus I, total incoming power, equal to sigma A T3 power 4, total outgoing power for the spaceship. You can understand this equation, and then I will just put the value of I here. Instead of I can write sigma a t2 power 4. So 2 sigma a t2 power 4 is equal to 2 sigma a t2 power 4 is equal to sigma a into t3 power 4. So from here you can see sigma a t3 power 4 equal to 2 sigma a into t2 power 4, or t2 is equal to t, so it is 2 sigma a t power 4. Sigma a gets cancelled out, so t3 is equal to fourth root of t3 is equal to fourth root of 2 into t. This result I have got after using one enclosure. If you use n such enclosures, so for one enclosures inside root I have got 2. For n such enclosures inside the fourth root I will get n plus 1. So that should be your answer. If you have some problem understanding this equation, you can also write the power equations for this enclosure and for this spaceship separately. For example, for enclosure, you can only write that what is the heat that is coming to the enclosure. It is sigma a t3 power 4 only, right? And the net heat that is outgoing from the enclosure is 2 times sigma a t2 power 4, right? So let us take this is one equation, and another equation for the space probe. For the space probe, you can see that the incoming power is I, and sigma a t2 power 4 is equal to sigma a t3 power 4. That equation already we have written here, right? Now if you solve this two equation, what you will see that sigma a t3 power 4 is equal to, this is equation number 1. So sigma a t3 power 4 is 2 sigma a t2 power 4. So if you combine these equations, then you can say I plus sigma a t2 power 4 is equal to 2 sigma a t2 power 4. From here also you can say sigma a t2 power 4 is equal to I, right? So that is the same equation I have written here. Otherwise, if you can understand that, it's just like a Gauss law, that what is the total power outcoming from any closed surface is only equal to the power source inside the surface, not the intermediate powers that are generated and coming to the surfaces. Only externally applied power source you have to take. I hope you have understood the solution, and if you could solve this question by yourself, then please leave a comment in the comment box that how much time you have taken to solve this question.